Friends, welcome back to TMRM Art YouTube channel. So now we are discussing the remaining technical 2-number questions, okay, of 2021 GATE ECE PYQ. So question is here, question number 43. An asymmetrical periodic pulse train V in of 10 volt amplitude with on time T on is 1 millisecond and T off is 1 microsecond is applied to the circuit shown in the figure. The diode D1 is ideal. Okay, the difference between the maximum voltage and minimum voltage of the output VO is, okay, this we need to find out. So here the difference between this maximum and minimum voltage of the output we need to find out. Now clipper circuit, what is clipper circuit? Here, like, it is a circuit that cuts the portion of the waveform which is given. Okay, suppose this is the input waveform given. Okay, here it is applied at input. Now if we apply this clipper circuit, then what will happen in the output? We will get like this. So some portion of the input is actually removed. Okay, here it is mentioned like the circuit that cuts the portion of the waveform. Now coming to calculation, initially assume that the diode is forward biased for the rising edge of the signal. Okay, so diode will be forward biased in the positive cycle. So here, like this diode, it is short circuited. Okay, here it is shown. So at t equal to 0, when the diode is forward biased, the circuit is like that. The capacitor changes to 10 volt in the positive half and VO is 0 volt. VO is 0 volt because here no voltage drop is there because it is shorted, so VO is 0 volt. Okay, and capacitor charges up to 10 volt. Okay, capacitor will charge up whatever the input voltage is there in the positive cycle, that is 10 volt. And during the negative half cycle, so negative half cycle, what will happen? The diode will be open circuited. Okay, the diode is reverse biased because in negative cycle, what will happen? Negative cycle means in the question actually it is mentioned T off, that means no signal applied. Okay, here actually 0, like the input signal is like this. For first 1 millisecond it is like this, and then the remaining it is off, like 1 microsecond it is off, then again 1 microsecond it is on, then 1 millisecond it is on, and this 1 microsecond it is off, and it goes on like that. The input is there. So the negative cycle means the off cycle, no input is applied, so whatever the charge is there inside the capacitor, that will continue discharging. Okay, that starts discharging. But here we can see by KVL, okay, plus VC plus VO equal to 0, so VO will be minus VC. So VO is minus VC, that means the diode is reverse biased. So it is open circuited. Now the capacitor will discharge through the resistor. So capacitor will discharge through the resistor. Now time constant is R into C. R also given and C also given. So time constant is coming this, okay, 10 millisecond, that means 10,000 microsecond. Time available is 1 microsecond. Okay, because in the negative half, or you can say the off cycle, this is 1 microsecond. Okay, so here VC will be how much after 1 microsecond during that off state, because VC will discharge up to 1 microsecond, because after 1 microsecond again on state will come. Okay, so up to 1 microsecond only capacitor can discharge. So we are checking VC after this 1 microsecond. Okay, so tau here actually one more 0 will come. So here if you see, this is 10 volt because, okay, here if you see, you can calculate, it is near equal to 10 volt. So capacitor never going to discharge. So in the next cycle the circuit will be again this one. Okay, again diode will be shorted and capacitor will be there, and the positive cycle of the input will be present. So what will happen? Every time in the T on and T off, it is shown actually. Okay, because in the T on it is output voltage will be always 0 because it is shorted, so output is 0, and T off we have seen that here output is minus of VC. So and VC charged up to 10 volt, so minus VC means minus 10 volt. Okay, so maximum minus minimum is 0 and minimum is that minus 10 volt capacitor voltage or output voltage, you can say, in the up cycle. So the difference is 10 volt. Now moving on the next question. For the transistor M1 in the circuit shown in the figure, mu1 Cux equal to 100 microampere per volt square and W by L equal to 10, where mu1 is the mobility of the electron and Cux is the oxide capacitance per unit area, W is the width and L is the length. So here one transistor is there, MOS transistor. The channel length modulation coefficient is ignored here. If the gate to source voltage VGS is 1 volt, to keep the transistor at the edge of the saturation, then the threshold voltage of the transistor is, the threshold voltage of the transistor we need to find out when the transistor is at the edge of the saturation and gate to source voltage is 1 volt. So MOSFET is in the saturation if VDS greater than VGS minus VT, we know this, and at the edge of the saturation VDS equal to VGS minus VT. So VDS equal to VGS minus VT at the edge of the saturation, and the drain current at the saturation, it is mu1 Cux W by 12 VGS minus VT whole square. Now calculation, let the threshold voltage of the MOSFET is VTH. So given mu1 Cux equal to 10 microampere per volt, so W by L here equal to 10, it is given actually. Okay, now we are applying the KVL here, okay, in the output loop. So we can see VDS, okay, VDS equal to this 3 volt minus here the voltage drop across this resistor, okay, 3 minus this 20 into IDS. This is second equation. First equation we need to derive here, like IDS equal to this drain current equation, and here just we are putting the values, and VGS already given 1 volt and VT, that is VTH threshold voltage, so it is coming this. So this is the first equation. Now from these two equation 1 and 2, like we are putting this IDS value here, okay, so this VDS will be 3 minus 20 into half into 1 minus VTH square. So from here if we want to simplify, here the VDS also equal to VGS minus VTH, okay, that is 1 minus VTH, because VGS already given in the question 1. So VDS equal to 1 minus VTH, so we can write in place of this VDS 1 minus VTH, and so the equation will be this, okay, you can see, and 1 minus VTH we are just taking as A for the simplification of the solution of this second order equation. So the A will be this, okay, minus B plus minus root over B square minus 4AC by 2A, and so there will be two possible values of A, but if we put A equal to 0.5, then 1 minus VTH is 0.5, that means VTH is 0.5, and if we put A equal to minus 0.6, then the VTH will be 1.6 volt, but VGS need to be greater than VTH. So only if VTH equal to 0.5, then only VGS greater than VTH possible, because VGS is 1 volt given in the question. So this is not possible, that means A's value is 0.5 only, so VTH also 0.5 only, okay. This is the correct value of the threshold voltage. Now notice, always try to convert drain current second order equation in terms of voltage, okay, in terms of voltage always try to convert this current equations, okay. We are converting here, you can see, in terms of voltage, especially threshold voltage, because okay, because out of the two values we can eliminate one value using this VGS minus VTH relation. Now next question. A circuit with an ideal op-amp is shown in the figure. A pulse V in equal to 20 millisecond duration is applied to the input, okay, you can see one input is applied of duration 20 millisecond. The capacitors are initially uncharged, okay, these capacitors are initially uncharged, means charge is 0. The output voltage V out of the circuit at t equal to 0 plus is, this we need to find out. Okay, here two method is there. So first method is, since we are applying at t equal to 0, okay, this input, So a short duration pulse it is. Okay, so at t equal to 0 minus v in 0. Okay, t equal to 0 minus this v in is 0 here, and vc 0 minus this is also 0 because initially uncharged already mentioned. Since vc 0 plus equal to vc 0 minus also 0 because capacitor cannot charge immediately or cannot change the voltage immediately. At at t equal to 0 plus, capacitors will behave as a short circuit. Okay, it will behave as a short circuit, sudden change, so it will be short circuit capacitor. So at t equal to 0 plus, v in is 5 volt. Since it behaves like an inverting amplifier, because here input is applied in the negative terminal of the op-amp, so it is inverting amplifier. So output is here minus R2 by R1 into Vn. Okay. Now R2 is this 10 kilo ohm and R1 is short circuited, so this is 0 kilo ohm. So output will be, if you put these values here, okay, then it will be minus infinite. Since output cannot be less than this minus V saturation, so output is minus 12 volt. Hence it will work like a capacitor only because capacitor only charge like fully charge, can fully charge with respect to the input after certain amount of time. So it is like working like a capacitor, you can say. Now method 2 is using the Laplace transform method. Okay, we are checking here C equivalent is like capacitors in parallel, so we are just adding the capacitances. Okay, 1 plus 1 equal to 2 microfarad. Okay, here, and in the S domain it will be 1 by 2s. Okay, and resistance is there. So by virtual ground concept we can see like it is 0 volt, it is also 0 volt, so VA is 0. So applying KCL at node A, VA minus this V out by 10, okay, and VA minus V in by this 1 by 2s equal to 0. Okay, so V out will be this. Okay, you can calculate here. Now the input voltage also you can write in terms of this unit step function. Okay, here it is from 0 to 20 millisecond and the amplitude is 5 volt. So amplitude is 5 volt, 5 is here, and so 1 unit step is here, and then minus up to 20 milliseconds. So another unit step starting from that 20 millisecond, we are just doing minus, which is starting from 0. So only this part will be remaining will be 0. So and in the Laplace domain it will be 5 by s 1 to 1 minus e to the power, this term is there, minus 20 into 10 to the power minus 3 into s. Okay, this we are putting here. So output will become this. Now applying the initial value theorem, so V out at 0 plus, it will be limit s tends to infinite s into V out s. Okay, so limit s tends to infinite s into this portion is there in the, okay, in place of V out. So the calculation by calculation you will get minus infinite. So again it cannot exceed minus 12 volt because of the saturation voltage is minus 12 volt in the negative side, so output will be minus 12 volt. This is the answer. So the output voltage V out of this circuit at t equal to 0 plus will be minus 12 volt. Now moving on the next question. Hope you are enjoying the video, and please like and subscribe for staying connected, okay, for future videos. The question is here, the propagation delay of the exclusive OR gate in the circuit in the figure in 3 nanosecond, okay, is 3 nanosecond here, propagation delay of XOR gate. Okay, the propagation delay of all flip-flops is assumed to be 0. Okay, this flip-flops propagation delay is 0. The clock frequency provided to the circuit in 500 megahertz. Okay, after 500 megasecond, one clock we are providing. Okay, I mean 500 into means within 1 second this much clock actually we are providing, that you can understand. So starting from the initial value of the flip-flop, okay, it is 111 and D2 is 1. So the minimum number of triggering clock edges after which the flip-flop outputs Q2, Q1, Q0 becomes 100 is. So after how many clock edges, okay, the flip-flop output becomes 100 from this we need to find out. Now the solution is clock frequency is this 500 megahertz. So T clock will be 1 by f, okay, that is this 2 nanosecond, okay. This is one clock period actually. So the first clock edge is here at 0 nanosecond, okay, and then here 2 nanosecond the second clock will come, and then 4 nanosecond here the third clock will come. Now any change or input per input, actually any change per input will occur at flip-flop output only at t equal to 0, 2, 4, 6, 8 nanoseconds, okay. T equal to 0, T equal to 2, T equal to 4, 6, 8 nanoseconds, the change will come in the output. So XOR gate delay is 3 nanosecond. So output at XOR will occur after 3 nanosecond. So XOR gate output will change after 3 nanosecond only. So as the delay is 3 nanosecond. Here you can see input at the t nanosecond, then output is t plus 3 nanosecond. So here this is same as D2 only, because the same thing is coming at D2. And the input of this XOR is this output of the Q2 and the output of this D, okay. This flip-flop and this flip-flop, okay. So here you can see the same thing. Now it is a right shift register, okay. Every time it is just shifting one bit right whenever the clock is applied, okay. So let's count it. Like first initial, this is the state of D2, Q2, Q1 and Q0. Now here we are doing XOR Q2 with Q0, and D2 we will get whenever the clock is applied, also 3 nanosecond after 3 nanosecond, because propagation delay of XOR is 3 nanosecond. Now here first clock is applied, so it will right shift, okay. But as means this one will be right shifted, and this will remain one only, okay, the first clock edge. And because it will change after 3 nanosecond only, so here you can see I have shown after 3 nanoseconds. So this is 1 second, 2 second, 3 nanoseconds. So after 3 nanosecond, this will change to what? This will change to the XOR of these two. So XOR of these two is 0, because XOR is inequality detector. So as these are equal, so it will come 0. Again, forget about this. Again, the means after this, like 1 second over, then we will see the same thing, because no clock edge is there. Now in the second actually, means after 2 seconds, here another clock will be applied. So here you will see what again right shift will be there, because here 1 is there, so it will be right shifted like this, and this will remain same. Okay, after 3 nanosecond again it will change. So here you can see 1, 2, 3. Here again it will change after doing these two XORs. Okay, these two XOR you will get this. Okay, similarly it will goes on. Actually I can explain it for this also, third second. So D2 will change only after 3 nanosecond from the clock applied. Okay, because I have already shown here after 3 nanosecond it will change. These are the input of the XOR gate, and here this is the output after 3 nanosecond. So same thing actually goes on here. For 3 nanosecond you can see it will change, and these ones will be same, because here no clock is applied, and then third clock will come, then it will shift here, and I mean this will shift here, this will shift here, this will shift here. Okay, again then fifth second it will be same. Okay, no clock is there. Now again fourth clock will be there, so it will be again right shifted, and it will remain same. Now again after 7th means 7th second it will be 1. Okay, because these two's XOR will come here. Okay, after this clock here 3 nanosecond over, so these two's XOR will be this. Okay, and remaining will be same. Now again after 8 second again one clock is applied, so it is right shifting is happening. Okay, and this will be remain same. and after 9 second again here you can see after this clock 3 nanosecond over, so these two XOR will happen, and here it is 1, and remaining things are same as there is no clock. So in the question it is asked actually minimum number of triggering clock edge after which the flip-flop output Q2, Q1, Q0 becomes 1, 0, 0. So minimum number of clock is 5. This is the answer. So here also I have shown with respect to these plots. Okay, you can see D1. Okay, it is changing after the first clock after 3 nanosecond, 1, 2, 3. Okay. And it is changing with respect to these inputs Q1, Q2 and Q1. So at this clock edge this is also 1, this is also 1, so this XOR will be there at the output. Same things actually goes on. Okay, I think this is Q2 and Q0 XOR, so Q2 and Q0 we need to check, not Q1, for finding this D1. Okay, now moving the next question. Question number 47. The circuit in the figure contains a current source, okay, driving a load having an inductor and a resistor in series with a shunt capacitor across the load. Okay, shunt capacitor is there across the load. The ammeter is assumed to have zero resistance. Okay, the switch is closed at time t equal to 0. Switch is closed at time t equal to 0. So initially when the switch is open, the capacitor is discharged. Okay, capacitors are discharged and the ammeter reads 0 ampere. Okay, so initially it's actually 0, means ammeter reading is 0 because there is no closed path, so input is not there, means capacitor already discharged. After the switch is closed, the ammeter reading keeps fluctuating for some time till it settles to a final steady state value. So after capacitor is some amount of like it reaches the steady state, okay, by charging with the source. After that it will be when it is in steady state, so the fluctuation will stop in the ammeter. Okay, so the maximum ammeter reading that one will observe while fluctuating ammeter, suppose here, so while fluctuating, what is the maximum reading that one will observe after the switch is closed? Okay, solution. Capacitor do not allow sudden change in the voltage, that is Vc0 minus equal to Vc0 plus. Okay, inductor do not allow a sudden change in current. Inductor do not allow sudden change in current, and capacitor do not allow sudden change in voltage. That's why Vc0 minus equal to Vc0 plus and IL0 minus equal to IL0 plus. Now when this switch is opened, okay, so at that time inductor current is 0, and so VL0 minus also 0. No current flowing means voltage drop is also 0. So as we know, when the inductor and capacitor both present, we use the Laplace domain concept like this. Okay, when they both present, we use the Laplace domain concept like this. So capacitor is like this, so Laplace domain it will be like Vc0 minus, and the capacitance is 1 by SC plus minus. And then inductor we can represent like this, plus minus Vc0 minus and 1 by I mean like this, not this, forget about this. this one. Okay, so here current will be flow like this, IL0 minus, I'm just removing this word. Okay, so IL0 minus by IS, here current source will be there, here voltage source will be there, and here S into L. Or we can represent like this. Okay, now the circuit for t greater than 0 in the Laplace domain, it will be like this. Okay, just we are converting in the Laplace domain all these things. Okay, just t greater than 0 when switch is closed. Apply. So at those moment, so voltages are these voltages are 0 actually, and current is 0, and these voltages are 0. So we are not including these things here in this circuit. Okay, now apply nodal concept. Okay, apply nodal concept we are applying here. Okay, so current is entering here and here one current is voltage by this. Okay, then this voltage by this one impedance. Okay, now here VCS we can calculate. VCS will find by calculation this one. Okay, and then okay, we need this IL is equal to then VCS by this total this path. Okay, if we get this VCS, then this VCS by this impedance, it will be this ILS. Okay, from the denominator part here we can see we can equate with the second order standard equation. Okay, in the Laplace domain, if you read the control system, this is the standard one, second order equation. Okay, characteristic equation. So by comparing with the standard second order equation, we can see this natural frequency is you can equate with this. So natural frequency will be this one, and here again this damping ratio will get this. Okay, by equating these two. Okay, and the values are given, so if we put the values we will get this. Now first maxima or peak overshoot formula is e to the power minus epsilon pi by root over 1 minus epsilon square. Okay, so if we put this value we will get this. Now steady state value of IL will be limit s tends to 0 is this one. Okay, steady state value means final value actually, so s tends to 0. Okay, in time domain, if you want to get the steady state value or final value, then t tends to infinite, but in the Laplace domain s tends to 0. Okay, and s need to be multiplied here, and this term is there, so it is 1. So at steady state the value is 1. Okay, it is mentioned here, and the overshoot is this one. Okay, maximum peak overshoot. So this you can see here, this upper point is at 1.44. so the maximum ammeter reading just after the switch closed is this one. Okay, I think you have understood here why we calculated the current, because we need the ammeter reading, and ammeter measures current only. Okay, now question number 48. A unity feedback system that uses proportional integral, okay, proportional integral PI control is shown in the figure. The stability of the overall system is controlled by tuning the PI control parameters Kp and Ki. Okay, the maximum value of Ki that can be chosen so as to keep the overall system stable. In the worst case, marginally stable. Okay, it is. So what we need to find out, the maximum value of Ki that can be chosen so as to keep the overall system stable, or in the worst case marginally stable. Okay, it can be stable, or worst case it is marginally stable. So we need to find out the maximum value of Ki. So obviously you can able to realize some Routh criteria will be involved here. So the GS is multiplication of this, and it is unit feedback. Okay, so multiplication you can get this. Okay, the characteristic equation will be 1 plus GS equal to this. Okay, now from the necessary condition, what is necessary condition? That for the necessary condition all coefficients must be positive. Okay, in this characteristic equation, necessary condition satisfied, the system may be stable. Okay, necessary condition not satisfied, then the system cannot be stable. So if necessary condition satisfied, that means all the coefficients are here, like you can see these are the coefficient here 1. All the coefficient must be positive. This is the first necessary condition to be stable, but it may not be stable. But if it is if all the coefficients are not positive, then it cannot be stable. Okay, so from the necessary condition, so Kp, okay, here if you equate this greater than 0, then you will get Kp greater than -1, and here if you equate this greater than 0, then Ki greater than 0. Now the Routh table we are writing s to the power 4, s to the power 3 square, s1, s to the power 0. So here 1, 5, and this one, then s cube, this is 4, and this term we are writing. Now here like that was these two multiplication, then minus these two multiplication divided by this. Similarly here these two multiplication, then this 2 here 0 is there, so divided by this, then it will come this. So same thing will be carry on. So s1 in this row it will come like this 2 multiply, then minus this 2 multiply of this 2, then whole divided by this. Okay, now whole divided by this, simplification of this is this. Okay, so after this calculation you will get this. Now for stability is there should not be any sign change. Okay, there should not be any sign change, so this term also will be greater than, this term should be greater than 0. Okay, and also this term should be greater than 0. So from here we are getting kp less than 9, and again from here for necessary condition we got this kp greater than -1. So kp's range is from -1 to 9. Okay, it is greater than -1 less than 9, and here we are getting this range. Okay, for the maximum value of ki, which we need to find out actually for our answer, so we need to do this derivative with respect to kp here. Okay, because ki is in terms of kp. So if we equate this to 0, then we will get this. So here kp equal to 4, so again we are putting this here, so we will get this one. Okay, so this is the maximum value of ki for which the system is stable, or worst case it is marginally stable. Now moving on the next question. The sinusoidal message signal having root mean square value of 4 volt and frequency of 1 kHz is fed to a phase modulator with phase deviation constant is this one. Okay, the carrier signal CT is this. The maximum instantaneous frequency of the phase modulated signal we need to find out. Okay, the general expression for a phase modulated signal is given by this SPMT equal to AC cos 2 pi FCT plus KPMT. Okay, this we need to remember, KPMT. Okay, and this whole part is theta I, instantaneous angle. So theta is the instantaneous phase, you can tell. Okay, maximum instantaneous frequency Fi is given by what? Fi equal to 1 by 2 pi d theta I by dt. Okay, d theta I by dt. Now this standard phase modulated signal is this. Okay, kp is 2 radian per volt, it is already given in the question. Okay, and mt is this one, am sin 2 pi fmt. Okay, we are just assuming this because it is mentioned a sinusoidal message signal is there. Okay, so given this am by root 2 is 4 volt. This is also given, like root means square of the message sinusoidal message signal is 4 volt. That means am by root 2 is 4 volt. Okay, and fm value also given. Okay, 1 kilohertz, and frequency is 1 kilohertz. Okay, that means 10 to the power 3 hertz. So mt equal to this 4 root 2. Okay, means this magnitude is 4 root 2 sine 2 pi the frequency t. So this is the message signal. Now this instantaneous frequency maximum is here 1 by 2 pi d theta by dt max. So d by dt, this whole term. Okay, now here mt also we know, kp also we know. Okay, and fc also given in the question. Okay, so the derivative will be like this, the result. Okay, and then again this also we can do the derivative, mt also we know, here we can do the derivative, and this will come like this. Okay, and the maximum value of this cos theta is 1. So just putting the value 1, now you can calculate and you will get this answer. Now the next question. Okay, question number 50. Consider a super heterodyne receiver tuned to 600 kilohertz. Okay, if the local oscillator feeds to 1000 kilohertz signal to the mixer, the image frequency is in kilohertz. Okay, we need to find out. Now what is super heterodyne receiver? This receiver changes any received radio frequency into a fixed intermediate frequency so that the amplification and filtering becomes easier and better. Okay, okay, I think you understand. The amplification and filtering will be easier and better, okay, if we use this super and receiver. For example, suppose received frequency like FRF is 1000 kilohertz, but desired intermediate frequency is this one, okay. Then local oscillator is set to FLO equal to 1000 plus 455, then it will become 1455 kilohertz. So the mixer output contains these two, okay, 1455 plus 1000, then it will be 2455 kilohertz, and again if you do minus, it will be 455 kilohertz. So the receiver keeps only the 455 kilohertz intermediate frequency and rejects the other frequency, okay. So like that, for this reason actually separator and receiver is needed. So the receiver is said to receive the radio station whose carrier frequency is here 600 kilohertz. This is just an example. Now here from the question, this is the receiver is said to receive the radio station whose carrier frequency, this is the carrier frequency of the radio station, okay. Okay, then it is coming here. Now local oscillator frequency is here 1000 kilohertz, okay. So here the distance is from here to here is 400 kilohertz, okay. So that means image frequency will be also after 400 kilohertz, that is 1400 kilohertz, okay. This so answer is 1400 kilohertz. Now the path is like antenna is there, transmitting antenna, then RF amplifier, okay, this is receiving antenna, then RM not transmitting antenna, this is receiving antenna. So then RF amplifier, mixer is there, then local oscillator will be there, then here intermediate frequency amplifier will be there, okay. Then detector or demodulator will be there, then audio amplifier will be there, then in the speaker we can hear the audio. Now moving on the next question. Please stay motivated and keep revising the concepts again and again, okay. Let's start this 51 question. In a high school having equal number of boy student and girl student, okay, for 75% of the students study science and remaining 25% students study commerce, okay. Commerce students are 2 times more likely to be a boy than a science students, okay. 2 times it can be boy, okay, for commerce. The amount of information gained in knowing that a randomly selected girl student studies commerce is dash bits, okay. This we need to find out, amount of information. So information we calculate in this form, okay, log base to 1 by p bits. So none of boys and girl students are equal, okay. It is mentioned in the high school equal number of boys and girls are there. So PB equal to 1 by 2 and PG also equal to 1 by 2. Now 75% students study science and 25% students study commerce. So probability of student study science means science student probability is 3 by 4 and commerce student probability is 1 by 4. Commerce students are 2 times likely to be a boy than are science student, okay. 2 times likely to be a boy than science student. Now probability that one commerce guy is selected and he is boy is 2 times more that probability of a science guy is selected and he is a boy. It is also given in the question, okay. Commerce students are 2 times more likely to be a boy than a science student. Just we are writing what is mentioned in the question. Now probability of being a boy is what it will be, probability of commerce student and he is a boy into probability of being a commerce student plus probability of science student and he is a boy and into probability of science student, okay. So this like we can get probability of being a boy and that is half because equal number of boy and girl is there. So this is half, and here also we know probability of commerce students is 1 by 4 and science is 3 by 4, okay. And this we can represent in terms of this commerce boy, okay. So this will be this 1 by 2 p of b by c. So from here we can get this p of b by c, okay. We will get this. Now p of c by b means selected a boy and he is commerce guy. So it will be this one, conditional probability. Okay, so P of B in the below, and upper it will be P of B by C into P of C. So all the things we know, just we need to put and we will get this. Now we know probability of a student like being commerce, means commerce student probability. We can write like this: probability of C by B into probability of B plus probability of C by G, means girl and commerce, and then probability of being a girl. Okay, then here this is also we know, like probability of commerce student is 1 by 4. Okay, now here we have calculated already this, being a boy and commerce student, and probability of being a boy and being a girl is half, and this part we need to solve. Okay, then after solving we are getting 1 by 10. This is not the answer. Now the amount of information gained in knowing that the randomly selected girl student studies commerce, this is log base to 1 by P of C by G. Okay, that means minus log base to P of C by G. So here if we put again 1 by 10, then again 1 minus will be outside, so minus log base to 10, it will be this bits. So this is the answer. Now moving on the next question. Okay, a message signal having peak to peak value of 2 volt, root mean square value of this 0.1 volt, and bandwidth of 5 kilohertz is sampled and fed to a pulse code modulation, okay, system that uses a uniform quantizer, and the PCM output is transmitted over the channel that can support a maximum transmission rate of 50 kilobit bps, okay, kilobit per second. Assuming that the quantization error is uniformly distributed, the maximum signal to quantization noise ratio that can be obtained by the PCM system. I think we have read the question. Now what are the terms here used? Normal noise is like noise added by the nature or the communication channel. Now quantization noise is noise created by the analog to digital converter because it rounds the signal. Okay, suppose the amplitude is 0.05329, it can take up to this, so it is quantizing, means it is rounding up, so there may involve some error. So for PCM, pulse code modulator, the noise power is given by in this formula, okay, del by 12. What is del here? Here this is peak to peak voltage by 2 to the power n. Okay, for calculating n, the bit rate, okay, and the bandwidth of the message signal is given as. Okay, so we need to find out this RB equal to NFS. Okay, this the bit rate formula. Okay, the sampling frequency. Okay, so Fs equal to 2 FM. This is Nyquist criteria. Okay, the signal power equal to RMS value of the signal square. Okay, now sampling is a measure that it measures the analog signal at a regular intervals. Okay, according to the sampling theorem, this Fs greater than equal to 2 FM. According to the sampling theorem, this Fs greater than equal to 2 FM. So Fs equal to the sampling frequency here, and FM is the maximum message frequency. For example, 2.1 volt, 2.8 volt, and 3.8 volt is there. So quantization will be like around each sampled value to the nearest allowed level. This introduces quantization noise. Okay, so after sampling, suppose this sampling is taken, means after some interval we have seen the amplitudes is this, okay, of the signal. Now we are rounding up those in the nearest values. Okay, it will become 2, it will become 3, it will become 3. Now encoding is convert each quantized level into a binary code. So this we are converting again some binary code, like it is 2, this is 3, this is also 3. So the output will be becomes like in this sequence, first this 2, then if it is 3, then it will be 3, then it will be 3, like that it goes on. Okay, I can, okay, sorry, this is 3 only. Okay, so it is right. Now the calculation part we are returning. Okay, so RMS value of the signal is 0.1 volt. Now signal power is 0.1 square, Okay, so bit rate is NFS, so n into 2 into fm, okay, using Nyquist criteria. Okay, now RB is 50 equal to n into 2 into 5. So RB is 50, it is mentioned here. Okay, RB is 50, it is mentioned here. Then n into 2 into 5. FM also mentioned in the question. Okay, bandwidth of the message signal. So from here we are getting n equal to 5. I think you got it, how we are calculating this n value. Now step size will be that peak to peak voltage by 2 to the power n. So 2 to the power 5, and peak to peak voltage already given in the question 2 volt. So it will become 1 by 2 to the power 4. Now the noise power will be this del square by 12. Okay, so this will be this. the required signal to the noise ratio will be signal power to noise power. Okay, that means this one by this one. This is signal power coming from here, so we will get this one. Now moving on the next question. Consider a polar non-return to zero waveform using plus 2 volt and minus 2 volt for representing binary 1 and 0 respectively. So it is transmitted in the presence of additive zero mean white Gaussian noise with variance 0.4 whole square. The priori probability of transmission of a binary 1 is 0.4. The optimum threshold voltage for maximum a posteriori receiver is dash volt. Okay. Now here this additive means noise is being added, and zero means zero means mean at the zero position. Gaussian noise always in like that shape. Okay. Now optimum threshold voltage for an additive white Gaussian noise function, the optimum threshold value is given by this. Okay, VTH equal to A1 plus A2 by 2 plus sigma n square by A1 minus A2 ln P of 0 by P of 1, where P of 0 is the probability of the error when 0 transmitted and probability of the error when 1 is transmitted. Okay, this P1 and P0. Calculation given that P1 this one and P0 this one already mentioned in the question. The variance of the noise is this one. Okay, the given that the binary 1 is represented for minus 2 volt, and for transmission of binary 1 is represented for plus 2 volt. Okay. Okay, here okay, sorry, one thing is here it is 0. Okay, for minus 1 binary 0 is represented for the minus 2 volt, and binary 1 is represented for plus 2 volt. Okay, and binary 0 is represented for minus 2 volt for the transmission of 1. Okay, no need to mix up. For minus 2 we are representing this as 0. Okay, and binary 1 is related to plus 2 and 0 is related to minus 2 volt. That is final. Now for the transmission of the binary 1, so A1 equal to expectation of x plus n. Okay, and A1 will be E of x plus E of n. Okay, given that the mean of the noise is 0, so E of n is 0. This is noise, n for noise, so expectation of noise is 0. Now A1 equal to E of 2 plus E of n equal to 2 plus 0. So A1 equal to 2. Okay, so E of x here x equal to 2. Okay, for transmission of binary 0, that is A2 we are calculating here E of x plus n. So here x is minus 2. Okay, transmitting 0 equal to E of n equal to minus 2. So here optimum threshold you can just put the values A1, A2, and this mean also given in this question. I mean the variance sigma square is given here, and A1, A2 values also we got, and then P values also here we just putting it is there in the question. Okay, this is mentioned 0.4, so other p of 0 will be obviously 1 minus 0.4, that is this one 0.6. so the formula only we need to remember here, okay, for this polar non-return to 0 waveform to calculate this map. Okay, optimum threshold voltage for maximum a posteriori. Okay, in this type of question, this formula actually we need to remember. I mean this one. Now question number 54. A standard air-filled rectangular waveguide with dimensions alpha equal to 8 semi, b equal to 4 semi operates at 3.4 GHz for the dominant mode of wave propagation. The phase velocity of the signal Vp, the value of Vp by Vc, where c denotes the velocity of light, is okay. So here we need to find out the phase velocity. I mean the phase velocity by c. So the phase velocity is given by Vp equal to W by beta. Okay, the W is the angular frequency, beta is the phase constant calculated for applied waveguide as this, like beta equal to root under omega square mu minus m pi by a square for parallel waveguide. This we can remember. Okay, for parallel waveguide this is the beta. So Vp will be this one. Okay, this W by beta is coming from here and W is there. So here just this omega we are dividing in the numerator and denominator both part. Again here also mu we are dividing, okay, root mu we are dividing both numerator and denominator. Now c equal to 1 by root mu, we know this. Okay, when epsilon, if it is 1, then c equal to 1 by root mu. So Vp equal to c by root under 1 minus m pi, this 1 by root mu will be c by a omega square. Okay, you can see from here, and this is also c. Also the cutoff frequency is defined as omega c equal to m pi by a c. Okay, we can remember for the this dominant mode. Okay, the cutoff frequency is this. Then 2 pi fc omega c, we can write this 2 pi fc is this. Then fc will be after calculation c by 2a when m equal to 1. Okay, now again putting this like Vp equal to c by this thing is there, and here c by 2a. Okay, c by 2a. Here omega c we are just putting this value, means m pi c by a, m pi c by a, this value we are putting omega c. Okay, omega c by omega. So and this is sin theta equal to omega c by omega. Okay, then Vp will be what, c by 1 minus this sin square theta. Okay, sin theta we are putting. So 1 minus sin square theta is cos square theta and root is cos theta. So this is valid for a rectangular waveguide also. Okay, this is valid for a rectangular waveguide also. Now given a is given, b is also given, f is also given. I am just showing you where it is given. A given, b given, and this also given. Okay, that f. The cutoff frequency here you already got, c by 2a. Okay, that is this. Now sin theta is omega c by omega. So we are putting this omega c, we have just calculated here. So omega c by f is given in the question, so it will become this. Now cos theta will be 1 minus sin square theta, it is this. So Vp by c. So Vp by c, here from this formula we can see 1 by cos theta. Okay, so 1 by cos theta is, means this value already we got, 1 by this, it will be this answer. Now moving on the last question of this session. An antenna with a directive gain of 6 dB is radiating a total power of 16 kilowatt. Okay, the amplitude of the electric field is in free space at a distance 8 km from the antenna in the direction of 6 dB gain. Okay, is volt by meter. Okay, so we need to find out what the amplitude of electric field in free space at a distance 8 km from the antenna in the direction of 6 dB gain. So directive gain is given here 6 dB, and if we convert it in normal form, it will be 10 to the power 6 by 10, so it will be 3.98. Now radiating power P rad equal to 16 kilowatt. So distance here it is given 8 kilometer. We know that the average power formula is this half of E naught square by this eta. Okay, so here half into E naught square by eta naught, and eta naught we know here for free space it is 120 pi. Okay, so P average formula is P rad into GD by area. Okay, P radiated into GD by area. Okay, so the formula is this same, the average power, that is the average power only. So we are calculating here E naught square, remaining term will be multiplied in the left side, and it will be here P radian given. Okay, then GD also here, then 120 pi, and this 2 multiplying here, then divided by 4 pi, and R is also there. Okay, so E naught will be this. Okay, this is intrinsic impedance of the medium, this eta naught eta. So this is the answer, last question of the day. And here if you see rounded up to 3 decimal places, so 3 up to 3 we need to write after decimal point. We need to take care of this. Thank you for listening me. Stay motivated and stay tuned in this channel for future valuable videos. Okay, thank you. Jai Hind.